Hi everyone, I am Anthony Usha, Assistant Professor from the Department of Aeronautical Engineering in Gojan School of Business and Technology, and I am going to explain about space applications, that is the Unit 5, and let's get into the unit wise deeply. Unit 5, Space Applications, which speaks about history of space research, spacecraft trajectories, basic orbital maneuvers with 6 orbital elements, Kepler's law and Newton's law of gravitation. Important topics I have breakdown from the unit are history of space research, artificial satellites upper atmosphere research, spacecraft trajectories, the 6 orbital elements, Kepler's law of orbits and Newton's law of gravitation. Early astronomical observations. Let's take a brief journey through ancient astronomy. We begin with the Babylonians, who meticulously recorded celestial events, laying the groundwork for predictive astronomy. Next, the Egyptians. The Egyptians used their observations of the stars to align their pyramids and create a 365-day calendar, which is essential for agriculture and religious events. Moving on to the Greeks, who brought a new level of philosophical and mathematical reasoning to astronomy, most notably through thinkers like Ptolemy and Aristotle. The Chinese made detailed records of solar and lunar eclipses, contents, and supernova, some of the longest continuous astronomical records in history. Finally, the Mayans, which has developed an incredible precise calendar system based on detailed observation of the sun, moon, and the planets. So each of these civilizations played a vital role in shaping our understanding of the cosmos. Early astronomical models and ancient observations. From ancient times, civilizations like Babylonians, Egyptians, Greeks, Chinese, and Mayans observed the night sky. Their keen interest in celestial bodies led to the development of early calendars and laid the foundation for astronomy. In the 2nd century, the geocentric model was proposed by Ptolemy. This model placed the Earth at the center of the universe with the planets and stars revolving around it. It remained the accepted view for 1,000 years. Then came a revolutionary idea in the 16th century. Nicholas Copernicus introduced the heliocentric model, which placed the sun at the center instead of the earth. This radical shift reshaped the humanity's understanding of the cosmos. These models marked significant milestone in the journey of astronomical discovery, guiding the transition from myth to scientific reasoning. Rocketry developments. Our journey into space began centuries ago. In the 13th century, China was the first to use rockets, not for explorations but for ceremonial displays and warfare. Fast forward to the 20th century, where rockets evolved to become powerful enough to overcome Earth's gravity, marking the beginning of space capable technology. In the post World War II era, the United States and the Soviet Union pushed rocket technology further through intense missile development programs. By 1948 to 49, the V-2 rocket, initially built for war, was repurposed for science. It carries detectors that successfully recorded solar X-rays, opening new frontiers in space research. Each step paved the way toward the modern era of space exploration. Bridging Cold War divides in space research. During Cold War era, space research was divided between two major blocks, that is East Bloc consisting of Eastern countries and the West Bloc made up of Western nations. Despite geopolitical tensions, scientific progress continued on both sides with major advancements in satellite technology, space probes, and exploration missions. To bridge the divide, the Cosper collaboration. the Committee on Space Research was established. It promoted international scientific exchange, encouraging both blocs to share research findings, collaborate on missions, and maintain peaceful cooperations in space. These collaborations become a symbol of unity through science fostering global progress in space explorations beyond political boundaries. Scientific revolutionaries and discoveries. The scientific revolution in astronomy was shaped by the contributions of three great minds. First, Galileo Galilei, often called the father of modern observational astronomy. In the early 17th century, he was used as a telescope to study the celestial bodies, discovering moons around Jupiter and supporting the heliocentric model. Next came Johannes Kepler, who formulated three laws of planetary motion. His precise mathematical description showed that planets orbit the sun in ellipses, not perfect circles, challenging long held beliefs. Finally, Isaac Newton unified these ideas through his monumental work, The Principle. He introduced the law of universal gravitation, explaining the forces behind Kepler's law and Galileo's observations. Together, their discoveries laid the foundation for classical mechanics and transformed our understanding of the universe. Early rocketry and space race. Tsiolkovsky's theory. Tsiolkovsky's theory's vision. In the late 19th and early 20th centuries, Konstantin Tsiolkovsky, a Russian scientist, theorized about space travel and proposed the use of rockets for explorations. Next, Goddard's liquid fuel rocket. Robert H. Goddard, an American physicist who launched the first liquid fueled rocket in 1926, laying the groundwork for modern rocketry. V-2 rocket development. World War II and the V-2 rocket developed by Nazi Germany. The V-2 rocket became the first human-made object to reach the edge of space in 1944. Milestones in space explorations. The space race, an era marked by intense competition between the United States and the Soviet Union, began with the historic launch. On October 4, 1957, the Soviet Union shocked the world by launching Sputnik 1, the first artificial satellite to Earth orbit. This event marked the dawn of space explorations. Just a few months later, on January 31, 1958, the United States responded by launching Explorer 1, its first successful satellite. This mission also discovered the Van Allen radiation belts surrounding the Earth. Then came a giant leap in human spaceflight. On April 12, 1961, the Soviet cosmonaut Yuri Gagarin became the first human to orbit the Earth, making a single loop around the planet in the spacecraft Vostok 1. The ultimate achievement came on July 20, 1969, when Apollo 11 successfully landed on the Moon. The American astronaut Neil Armstrong took the historic first step in declaring that's one small step for man, one giant leap for mankind. Space exploration milestones. Between 1962 and 1973, the Mariner missions explored our neighboring planets, that is, Venus, Mars, Mercury, sending back the first close up images. In 1977, Voyager 1 and 2 were launched to study the outer planets and still transmitting data from interstellar space. By 2000, a new era began with the International Space Station becoming continuously inhabited, marking a global collaborations in living and working in space. These milestones reflect humanity's growing research and reach into the cosmos, starting with flybys and leading to permanent space presence. Modern space exploration overview. Space exploration today is advancing faster than ever. Mars rovers like Spirit and Curiosity continues to uncover secrets of the red planet. Privacy spaceflight has taken off with companies like SpaceX leading the innovations in reusable rockets and commercial missions. NASA's Artemis program aims to return humans to the moon, paving the way for deeper space missions. Together, these efforts mark a bold new chapter in humanity's journey beyond the Earth. Astronauts' milestone in space exploration. On April 12, 1961, Yuri Gagarin made history as the first human in space orbiting the Earth above Vostok 1. Just 8 years later, on July 20, 1969, Neil Armstrong became the first person to walk on the moon, defining the moment in space history. In 1971, the Soviet Union launched Salyut 1, the world's first long-duration space station. By 1973, the United States responded to Skylab, which was inhabited for 24 weeks. These milestones marked humanity's bold transition from spaceflight to living this place. Journey to the Stars. Space probe milestones. In 1977, NASA launched Voyager 1 and 2, beginning a journey beyond our solar system. Voyager 1 entered the solar interstellar medium in 2012, followed by Voyager 2 in 2018. In 2019, Pioneer 10 approached the edge of the heliosphere, expanding our frontier in deeper space. Looking ahead, New Horizon is expected to cross into interstellar space by 2040. By 2060, Pioneer 11 may follow, continuing humanity's explorations far beyond our solar neighborhood. These spacecraft are carrying our message to the stars. ISRO's journey through space explorations. In 1969, ISRO was founded by Dr. Vikram Sarabhai, laying the foundation for India's space journey. By 1975, India launched its first satellite Aryabhatta, followed by the Rohini satellite in 1980 using SLV-3. In 2008, Chandrayaan-1 made history by confirming the presence of water on the moon. Then in 2013, Mangalyaan became the first Indian mission to reach Mars orbit on its very first attempt. Finally, in 2023, Chandrayaan-3 successfully achieved a lunar landing, marking a proud milestone for India in space exploration. Space observatories and their missions. The integral mission focuses on gamma ray studies, helping us understand extreme cosmic events like black holes, neutron stars, and supernovas. Meanwhile, the GEMS mission was designed to study X-ray polarization, revealing more about black holes and supernova remnants. However, GEMS was cancelled due to budget and time constraints. Despite the cancellation, its scientific goals remain highly relevant, inspiring future missions. These projects deepen our understanding of the most powerful forces in the universe. Space observatories and their functions. NASA's UARS missions helped us understand and monitor the Earth's atmosphere in unprecedented detail. Parallelly, the Great Observatories program was launched to explore the universe in different wavelengths. These include the Hubble Space Telescope for visible light, Compton for gamma rays, Chandra for X-rays, and Spitzer for infrared. Together, these observatories revealed the full spectrum of the universe, giving us a deeper view of galaxies, black holes, and distant stars. This multi-session and mission this approach transformed space science forever. Space research on space stations. Research in space serves a vital purpose. It allows us to study how the space environment affects the human body, conduct unique and experiments not possible on Earth, and test the technologies critical for future missions to the Moon, Mars, and beyond. In microgravity, scientists explore several disciplines. In biology, they examine how cells grow and how microbes behave, leading to insights into health and disease. In physics, the lack of gravity helps researchers study fluid dynamics and combustions in entirely new ways. Material science benefits too, with crystal growth and allow formation improving significantly in space, offering better quality material for use on Earth. And in medicine, astronauts help study bone loss and muscle weakening, conditions like that mirroring aging and osteoporosis. So together space research not only fuels explorations but also improves life on Earth through scientific innovations. Mir Space Station, a pioneer in space living. In 1986, the Mir Space Station was launched by the Soviet Union, marking a major milestone in human space exploration. It became the first modular space station hosting astronauts for extended missions. From 1986 to 2001, Mir was operated by the USSR and later Russia, supporting groundbreaking scientific research in orbit. After 15 years of space, the station was decommissioned in 2001, ending an era of pioneering long-term space habitation. So Mir paved the way for future stations like the ISS, International Space Station. A pioneer in space living. International Space Station ISS is the largest and most ambitious space laboratory ever built. Launched in 1998, it represents a multinational collaboration between NASA, Roscosmos, ESA, JAXA, and CSA. Orbiting about 400 kilometers above Earth, the ISS serves as a platform for continuous human presence in space, with astronauts living and working abroad for over 2 decades. It has hosted more than 3,000 scientific experiments across fields like biology, physics, medicine, and material science, many of which are impossible to conduct on Earth. So the ISS is not just a symbol of international cooperation but a critical testbed for technologies and systems needed for deep space explorations, including missions to the Moon and Mars. Through the ISS, the humanity continues to push the boundaries of science, technology, and peaceful collaborations in space. Spacecraft trajectories and its maneuvers. A trajectory is the path a spacecraft follows as it moves through space. It is determined by the spacecraft's initial velocity, gravitational force, and thrust from engines. Spacecraft trajectories and maneuvers refers to how a spacecraft moves through space and the techniques used to change its motion or path. Trajectories and maneuvers refers to how a spacecraft moves and basically classified into the categories which are comes under suborbital, orbital, and escape trajectories. Orbital trajectories include low Earth orbit, medium Earth orbit, geostationary orbit, and polar or sun synchronous orbit. Escape trajectories take spacecraft beyond Earth's gravitational pull, leading to interplanetary travel. These use methods such as Hohmann transfer for efficient orbit changes or gravity assist to gain speed and reach distant planets. Advanced maneuvers. Which advanced maneuver or concept should be used for the mission? Orbital maneuvers, which is suitable for adjusting orbital parameters and efficient transfers. Constant thrust trajectory, which is ideal for high thrust missions or deep space probes. Low energy transfers, which is best for fuel efficient but time consuming routes. Comparison of space trajectory. Space mission follows different types of trajectories, each with unique characteristics. Suborbital paths like Blue Origin, New Shepard re-enter the atmosphere and follows a partial ellipse or parabola. Orbital trajectories such as those of the ISS or GPS satellite complete continuous orbits in LEO, MEO, GEO or polar patterns. Escape trajectories leave planetary gravity for deep space missions. Using parabolic or hyperbolic paths, interplanetary trajectories travel between the planets as seen in Mars orbitary or Voyager probes, often using Hohmann transfer and gravity assist. Finally, transfer orbits such as Hohmann or bi-elliptic change a spacecraft's orbit with 2 or 3 burns. Introduction to orbital elements. Orbital elements describe the unique path of a celestial object. They define the object shape, its orientation in space, and its exact position at a given time. These parameters feed into celestial mechanics, which explains the motion of objects under gravity in a two-body system, such as a planet and a satellite. These principles and the Keplerian motion predicts mathematically define the path that govern how objects can move through the space. Elements defining spacecraft trajectories. 6 key orbital elements define the motion of a satellite. The semi-major axes determine the orbit size, while eccentricity defines its shape. Inclination measures the tilt of the orbit relative to the equator. RON, or right accession of the ascending node, specifies where the orbit crosses the equator heading north. The augment of perigee pinpoints the closest approach point, and the true anomaly shows the satellite's exact position along its path at a given moment. Together, they describe an orbit completely. Kepler's laws of planetary motion. In the early 17th century, Johannes Kepler formulated his groundbreaking laws of planetary motion. In 1609, he published Astronomia Nova, introducing the first two laws. Planets move in ellipses and sweep out equal areas in equal times. A decade later, in 1619, Harmonices Mundi revealed the third law, linking a planet's orbital period to its distance from the Sun. These insights laid the foundation for celestial mechanics. In 1687, Isaac Newton expanded on Kepler's work with his theory of universal gravitation, forever changing our understanding of motion in the cosmos. So, these are the development in celestial mechanics. Kepler's law. In general, Kepler's law is of three types. One is law of ellipses, which explains the planets which move in elliptical orbits with the Sun at one focus. Law of equal areas. A planet with sweep out equal areas in equal time, which moves faster near perihelion. Law of harmonics. The square of a planet's orbital period is proportional to the cube of its average distance from the Sun. This is t square is proportional to a cube. Their impact. Kepler's law revolutionized our understanding of the cosmos. They validated the heliocentric model, proving that planet orbits the sun in predictable elliptical path. These laws laid the foundation for Newton's laws of motion and universal gravitation, linking planetary motion to physical forces. Today, Kepler's insights remain essential in modern orbital mechanics, guiding satellite navigation, space missions, and our exploration of the solar system. Newton's universal law of gravitation. Newton's universal law of gravitation, which is formulated by Sir Isaac Newton in 1687. The law describes as goes, every particle attracts every other particle in the universe with a force that is directly proportional to the product of their masses and inversely proportional to the square of the distances between them, which is formulated as F is equal to G into M1 into M2 is divided by the whole R square, which is F is the gravitational force where G is the universal gravitational constant, M1 and M2 are the mass of the objects, and R is the distance between the center of the two masses. Applications. Orbits, Kepler's law, and escape velocity. Orbits and Kepler's law. Newton's law, which provides a centripetal force for its orbital motion, which explains the orbital path, which is explained clearly by the Kepler's first law. In Kepler's third law, which is derived from Newton, the formula comes as t square is equal to 4 pi square a cube divided by gm, where the t is orbital period and a is the semi-major axis of the orbit. So then escape velocity. So escape velocity is formulated as v escape is equal to square root of 2gm is divided by the r, which is the minimum speed which is needed to break free from planet's gravity, which is generally 11.2 km per second for the Earth. Space applications and its significance. Why we are studying, where we are going to apply these things and all. So, what are the real world applications or orbits of planets and satellites? For example, Earth's orbits around the sun. We can able to learn about this. So, tides caused by the moon's gravitational pull, weight of the object, different planets. For each and every planet there will be a different weight, right? So then space mission trajectories, we can understand the space mission trajectories and its path and significance, lay the foundation for classical mechanics, unified celestial and terrestrial mechanics under one law, and the key to understand astrophysics, orbital dynamic and satellite motion. Einstein's general relativity concepts and applications. Einstein's general relativity gives the experimental proofs as we know that equal to mc square, where we can understand from here that Mercury's orbit's precision, gravitational lensing and time dilation, which are all depends on this relativity, and the real world applications are space missions, astrophysics and geophysics. And then limitation, high speeds, strong gravitational field. So these are the limitations which is based on relativity of Einstein. Thanks for watching. Thank you. I hope you all enjoy space applications topics and its videos. Thank you.